Welcome, ministers and policymakers, to this exclusive executive briefing. Okay, let's just dive right into this explainer, shall we? Today, we're taking a hard, data-driven look at scaling carbon dioxide removal. As leaders shaping future climate policy, you already know that hitting our Paris Agreement goals means we have to aggressively pull carbon right back out of the sky. But as we'll see today, the path to a sustainable climate is actually paved with some incredibly complex, hidden environmental trade-offs.
Because here is the monumental challenge we're facing. To limit global warming to safe levels, the science tells us we might literally need to remove up to 900 gigatons of CO2 by the year 2100. I mean, that is a staggering amount of carbon. But here's the paradox we really have to navigate. How do we extract all of that without completely destroying the Earth's absolute resource limits in the process? We absolutely cannot solve the climate crisis by accidentally triggering a massive ecological or resource crisis somewhere else.
So, here's our roadmap for today. First, we'll cover the core carbon removal dilemma. Second, we'll look at chemical removal and its hidden mineral bottlenecks. Third, we'll examine biological removal limits. And fourth, we'll wrap up with priority recommendations for your ministries.
All right, let's start with part one, the carbon removal dilemma.
Now, what's really interesting about how we categorize our strategic options is that they basically fall into two distinct camps. On one side, we have chemical carbon dioxide removal. Think heavy industrial infrastructure like direct air carbon capture and storage, or DOCS, and ocean liming. On the flip side, we have biological carbon removal. These are methods like BCS, biochar, and large-scale forestation, which basically rely on nature's own processes to draw down that carbon.
But here's the core dilemma you really have to weigh. It's a classic trade-off. If we choose to scale up chemical technologies, we are fundamentally spending our global mineral budget because those facilities require massive amounts of mined materials. But if we lean heavily into biological technologies, we're spending our planetary nutrient, land, and ecosystem budgets. There is no silver bullet here, folks. Every single negative emissions technology just shifts the burden onto a different part of the Earth's system.
Let's move on and see how this builds into part two, chemical carbon removal, and its specific mining bottlenecks.
Take a look at this stark statistic from our data modeling: 86%. If we actually rely on direct air capture to meet our 2050 carbon removal demands, it could consume up to 86% of current global nickel production. Let that sink in for a second. Nickel is a vital strategic resource for our entire green transition. It's absolutely crucial for batteries, robotics, digital tech, the whole shebang. Scaling DAXIs to the level we need means the carbon removal industry will be in fierce, direct competition with the electric vehicle and renewable energy sectors for the exact same metals.
And this brilliantly illustrates the steep, resource-heavy trajectory we're looking at. Scaling up these chemical systems also drives up the extraction of barium by up to 77%. Why? Because it's heavily used in the well drilling required to build and power these massive chemical plants. It turns out we can't just drill our way out of a climate crisis without creating a massive global mining boom in the process.
Which brings us to part three, biological limits, specifically ecosystems and nutrients.
Switching gears to the biological side, here is another massive bottleneck we absolutely have to account for. Bioenergy with carbon capture and storage, BCCS, relies on growing enormous amounts of biomass. To meet the fertilizer demands for all those new crops, global potassium mining could spike by an incredible 70%. We're talking about an additional 23 million tons of mined potassium just to feed the plants that feed the carbon capture machines.
So, the crucial point is this: biological methods demand immense amounts of fertilizers and water. Beyond potassium, scaling things like BCCS and biochar puts high risk on global phosphorus and magnesium supplies. And remember, those are critical raw materials currently dominated by foreign markets, notably China. On top of that, the immense freshwater requirements for these energy crops exert dangerous pressure on planetary limits. By leaning too hard on biological carbon removal, we literally risk putting our climate goals in direct competition with global food security.
And we also have to look really closely at the collateral damage, even from practices we generally consider to be universally positive, like planting trees. Our data shows that large-scale forestation actually creates net health damages globally. This is largely due to the increased risks of forest fires in a warming world, and all that resulting fine particulate matter being released into the air. By 2050, the health impacts from these secondary effects are roughly equivalent to 0.5% of the global health damages caused by the COVID-19 pandemic in 2021. It's a sobering comparison, but it clearly demonstrates that there are no-regret solutions here. Even planting trees requires careful localized risk management.
Okay, finally, part 4, priority recommendations for your ministries.
Based on all this data, we've distilled 3 specific actionable imperatives. First, prioritize emission reductions above all else. Because every single carbon removal technology comes with severe side effects, we simply must reduce the absolute amount of carbon we need to remove by accelerating direct decarbonization. Second, build resilient mineral supply chains. If you are banking on chemical DACs for your net zero targets, you must immediately secure supply lines for strategic metals like nickel and critical materials like barium. And third, deploy regionalized portfolios. We can't scale biological methods blindly across the globe. They have to be strictly regionalized, implemented only where local water and nutrient resources can safely support them without threatening local food systems.
So this brings us to our final high-stakes consideration. The models prove we can make the carbon math work on paper. But as we wrap up this explainer, the real question you must ask yourselves as policymakers is this: are we prepared to sacrifice our absolute resource limits just to make that math work? Or will we craft a strategy that balances our climate survival with the health of the entire Earth system? Thank you so much for joining me today. I hope this intelligence empowers your next crucial steps.